what is the next type of control that we can look at, like to essentially alleviate this problem? Yes? I'm sorry, what is that? 24.5 you said. Sorry, yeah. Suppose if I want to essentially set my desired temperature as 25 degrees Celsius, right? Let's say the temperature is coming down from 30 degrees Celsius, right? If the room's structure is such that it fits in a certain class of systems, which we'll learn about later, maybe in the next, maybe after 4 or 5 lectures, what will happen is that the proportional controller may bring the temperature to 25.5 degrees Celsius down from 30, but it will never go to 25 exactly, or it may not go as close to 25 as possible. Okay, so that is a steady state error, right? Is it not, right? So for example, let me draw a diagram. Let's say like I want, let's say I plot output versus input, right? Okay, so let us say like I want a temperature of 25 degrees Celsius, right? What the proportional controller may do is that, like, starting at 30 degrees Celsius, it may essentially bring it down, but then it will settle down like this. So as time increases, you are going to have a non-zero steady state error. Okay, so that's what I called as a tracking error. What is tracking? Like, because I want to follow a certain set point, right? So, or even a time varying reference input, right? So that's tracking, right? So essentially, we will not be able to achieve zero steady state error. Okay, that's a limitation. Okay.
Therefore, it should be in the first on-off controller. Mod ET should be less than even, right? Because on both the sides.
Yeah, you can have, as I told you, you can have different variants. Absolutely. Okay. Yeah. You can have mod of E, right? So absolute value of E. Okay. Or one may say that, look, like, even if it's negative, I will do this. If it's positive or this one, depending on the value of E1, E1 can be negative. So that's why I said there can be many variants. Okay, you can give range. But then the thing is, like, you take these discrete actions. It's not like continuous action based on the error magnitude. Okay, you have like a discrete binary operation, right? That's it. But you look at a proportional control, it's a continuous action, right? At each instant of time, depending on the error, you take action, right? And the biggest advantage of proportional control is its simplicity, because the control input at any instant depends only on the error at that instant. That's it. You don't worry about the past, neither do you worry about what may come in the future. Okay, it only lives in the present. That's it. Okay, that's a big advantage of proportional control, right? Okay, then let's go to integral control. Okay, integral control is abbreviated by I. Okay, so that's the abbreviation used for integral control. Okay, so what is this integral control? As the name suggests, so you just take the control input u of t to be integral of the error, right, over a time interval. So you just take ut equals e tau d tau, and then you multiply it by a constant ki. Okay, ki is once again a real number. Okay, ki is what is called as an integral gain. Okay, so if we take the Laplace transform, what happens to this? What is the if you use the real integration theorem, right? What happens here? What is the Laplace of integral 0 to t e tau d tau? Es by s, right? So 1 by s gets multiplied. So this guy becomes u of s is ki by s e of s. So this tells me that c of s is going to be equal to ki by s. Okay, so this is the structure in the time domain for this particular controller, and this is the transfer function of this particular controller. Okay, the integral controller. Okay, right? Okay, now what are the pros and cons? Can, of course, at least in theory, okay, can lead to zero steady state errors. Okay, that's a big advantage why we use integral control. Okay. Okay, so we'll see how it does it, as I told you, right? So it can lead to zero steady state error. Okay, so that's a big advantage of integral control. But then, like, it should be used judiciously. Why? Because if you look at the integral controller transfer function itself, you will see that it has a pole at 0. See, if you look at C of S, right, ultimately what's going to happen, we discuss open loop pole and closed loop poles, right? Open loop poles are poles of the G of S times H of S. C of S is going to go in G of S, isn't it, right? So the moment I put a transfer function of the form Ki by S, I am going to introduce an open loop pole at S equals 0, right? So then we will see that, the control design for the closed loop system becomes a bit challenging. Okay, we need to be a bit more careful, because see, the control design, like we are only going to look at the open loop transfer function. My plant may not even have a pole at the origin, right, to begin with. The plant may be stable, but the controller structure which I am choosing can make it unstable, right? That is, the product of the plant and the controller transfer function will now have a pole at the origin. That means I will have an open loop pole at the origin, right? So then I need to be careful in stabilizing the closed loop control system, right? So this introduces an open loop pole at origin, okay, which essentially needs to be accounted for. And more interestingly, like integral control, like can lead to actuator saturation. Okay, so that's something which also we need to worry about. Okay, like when we do integral control. So what do I mean by this? Okay, let me demonstrate it by means of a graph. Let us say, like suppose, I consider a scenario, right? Let's say once again of this temperature control. Okay, let's say my initial temperature is 30 degrees Celsius. I come in, I set my temperature at 25 degrees Celsius, desired one. So let's say initially the error is 5 degrees Celsius, right? What happens from 5 degrees Celsius, like the error is going to keep on decreasing. Okay, let's assume that the error remains non-negative all the time, just for the sake of argument. Okay, now what would integral control do? Let's say now this is my current time t. Okay, let's say t1. Let me take an instant t1. Right, what will be the control input calculated by the integral controller at time t equals t1? It will be integral 0 to t1 e tau d tau. And graphically, what will be that? It would be the area, right? So now let's say I go to an instant t2. What will that be? It will be this area. So now what can you observe? Assuming that the error doesn't vary, right, between positive and negative, let's say it remains the same sign, right? What can happen is that this area can keep on increasing. If the area keeps on increasing, what do you think will happen to u? Keeps on increasing, right? Of course, you multiply by ki, but then with as time progresses, okay, you are decreasing the error. You are decreasing the error's magnitude, but the integral action takes into account the past error also, right? Because integration in a certain sense takes into account the history of errors, right? That's what it's doing, right? So essentially we are taking into account past errors and we are carrying them forward with us. Then what happens? We are going to face a situation where the area becomes so high that the control input may become very high that it can exceed the capacity of the actuator. See, for example, in this air conditioner, what is the actuator I may use? I will be using a compressor based cooling system, right? Let's say, like I have a certain capacity for the compressor and the fan assembly, right? And I keep on calculating this control input, okay, even as the temperature error goes close and close to 0, there may be a point where I may have a saturation in the control input. Okay, I may ask for, let's say, X liters per minute, okay, but the capacity of the system, the actuator may be less than X liters per minute, right? That may be possible. Okay, so that is also another limitation with integral control. So we need to be a bit more careful. Okay, so this is what is called as actuator saturation. Okay, like when you design integral control, so you need to plot the control input and check whether you are you are able to maintain your control inputs within the allowable bounds of operation. Okay, that's a check we need to do. Anyway, when we do control design, we will do all these things. Okay, so when we do control design, not only we are interested in making sure the error goes to 0, but also in ensuring that the control input that we are giving to the system is within practical bounds, right? Otherwise, there is no point, right? See, for example, if I want to have a linear motion system, right, in some machining assembly, right, and I purchase a motor system based actuator, electromechanical actuator, which can provide a maximum of 100 newtons. Now I program a controller which at an instant of time asks me for 1000 newtons. I can't realize it in practice, right? Then what will happen? I reach actuator saturation. Then with such a controller, although in theory I might be satisfying some performance requirements, in practice I would not be able to reproduce those performance requirements, right? Would I be? Right? Because I may say, hey, settling time would be so much with 1000 newtons. Peak overshoot would be lower than, let's say, 5% if you give 1000 newtons, but my capacity of the actuator is only 100. So in theory, while designing, I can put in whatever value I want, but we need to be realistic, right? As far as maintaining the control input within the actuator range is concerned. Okay, so that's something which we will also look at. Okay, when we do integral control. Fine. So that is the second block. Now, what is the third building block which we can use, which is what is called as the derivative controller. Okay, derivative controller abbreviated as D. Okay, so what do you think derivative control does? It differentiates, right, as the name indicates. It differentiates the error at each and every instant of time and then multiplies it by a constant, okay, Kd, which we call as a derivative gain, okay, and of course Kd is once again a real number, right, and then calculates the control input. Okay, so that's what it does. So if we take the Laplace transform, of course we neglect the initial conditions, then what will we get? We will get yes. Okay, so then the controller transfer function becomes Kd times S. Oops. Okay, that's what happens. Okay, so the controller transfer function is Kd S. So if you look at the derivative controller as a block itself, transfer function, you see that this is not a proper transfer function. See, if you incorporate the derivative controller as a block, as C of S in your block diagram, if you look at the controller transfer function as a standalone transfer function in its own right, you see that KDS is not a proper transfer function, right? What is a proper transfer function? The order of the denominator must be greater than or equal to the order of the numerator. So here the order of numerator is 1, order of denominator is 0. So this is not a proper transfer function, but then anyway when you put it together, we want the open loop transfer function to be a proper transfer function. That typically would work out, okay. So that should be kept in mind. So for example, if your plant transfer function had n equals m, okay, and you don't have h of s, you have to be 1. You can't obviously use the derivative controller. Why? Because the open loop transfer function will not be proper, right? So we need to keep that in mind, okay. So, but that's something which I want to alert you about. So let me repeat that. Suppose if you had your plant transfer function P of S to be a proper transfer function with n equals m, there can be scenarios like that, right? The order of the numerator and denominator polynomials of the plant transfer function P of S, let's say they are equal, right? And h of s happens to be 1, unity feedback. Then if you put C of s to be KDS, then you calculate the open loop transfer function G of s, H of s. you would have the order of the numerator to be one order more than the denominator, right, due to this KDS. Then we need to be a bit careful, right? So we can't really use that, right? Yeah. So, but typically, the open loop transfer function would become proper, okay? And this is what the derivative action would lead to, right? So essentially, it would lead to this transfer function, right? But physically, what does the derivative controller do?
The error is going to change more in the future, then it will do a higher correction.
Okay, very good. So if you look at the derivative action itself, right? So let's say you take any time t. What's going to happen is that the derivative is going to calculate the slope of the error, right? So in a certain sense, it's peeking into the future, right? The derivative, the sign of the derivative and also the magnitude of the derivative would tell me what is going to happen to the error in the next instant, right? So in a certain sense, the derivative controller leads to an anticipatory response, okay? Like, so it tends to peek into the future, okay, and take corrective action. As he said, let's say if the error is going to increase a lot, then maybe it may take action now itself, so that like it will not allow the error to increase beyond a certain limit, right? If we know that the error is on a downward trend, then I will progressively reduce the control input. Now, why should I add? See, control input has to do with cost, ultimately, in real life, right? See, let's say you are running a compressor, we are spending for electricity, right? Is it not, right? If I know that, like my temperature error is decreasing, I would essentially, run my compressor at a lower setting so that I can save cost, right? So, obviously, the derivative controller can do these, can satisfy these functionalities, right? But what are potential limitations with derivative control?
It can lead to non-zero tracking error.
Non-zero tracking error?
Non-zero steady state.
Non-zero steady state error?
So because as soon as the error reaches a certain value, it remains constant, the controller won't be able to track it.
Okay. So, in other words, you will see that derivative, controller will not take any action. Suppose if the error reaches a constant non-zero value. See, let's say the temperature error due to some reason, let's say falls down to 2 degrees Celsius and remains there due to whatever reason, right? In practice, we cannot control what may happen, right? Imagine a scenario where it becomes constant. Then what is the derivative of a constant? Becomes 0, right? So, okay, that is one perspective, what he told, right? So, but more importantly, any other concern that we may have from derivative control? We look at from a response characteristics perspective later, but we are now looking at more like an intuitive, trying to get an intuitive understanding, right? It will make it unstable. Oh, that once again maybe if you have sharp changes in the error, you may exceed the actuator's limits. Okay, agree. See, more importantly, those are all important aspects. Okay, as he told, if you have constant error, the derivative controller will not take any action or will take negligible action, right? See, error may not exactly remain constant. Okay, let's say if it essentially hangs around a constant value, derivative controller may not be able to take sufficient action. And as he told, if you have a discontinuity in the error, not even a discontinuity, sudden change in the error due to whatever reason, okay, the derivative controller may essentially give very high inputs, okay, which may be beyond the actuator's limits. See, for example, let's say I have an air-conditioned room. Suddenly, it's in the peak of summer. Suddenly I keep the door open for 2 minutes due to whatever reason. What's going to happen? The thermal load is going to increase a lot, right? The error is going to shoot up, right? Then the derivative controller will try to use the maximum capacity of the compressor, right? So, question is whether it's desirable or not. Okay, that's a different question to ask. Okay, but that's the characteristic of the derivative controller. But I'm going to essentially leave you with one more limitation of derivative controller with this example. Okay, once again, it's just a numerical example to just convey the point. Okay, let us say your error was something like let's say sin t plus 0.01 sin 100t. So what this means is that let's say I have an error signal. Okay, once again this is just a notional example to convey the issues with derivative control, right? So let's say my error essentially oscillates as sin t. Okay, but what is sin 100t? It is high frequency noise, right? In practice you always have noise coming in through measurements, right, in real systems. See, even if you take an oscilloscope, you measure a constant voltage signal, do you get a nice smooth line? No, you will get a band, right? So let's say like you have a band which is your noise, right? So this has a band. Okay, so I am just to just demonstrate the concept, I am just what to say, doing this. So now if you, let's say you take the derivative of this, what will happen is that you will get cos t plus what will happen to the other term? You will get cos 100t. Okay, so what should have been my derivative signal in the ideal world? It should have been only cos t, okay, which will be like this. That should have been my ideal derivative signal, which should have been the control input. But what is cos 100t? Extremely fast cosine signal, right? And cosine 100t is going to mask this cos t. Do you agree? So cos 100t is going to be something like, like let's say it's going to be like a band. Okay, we will not even be able to, I'm just drawing relative to this. Okay, so but you get the point, right? So it's going to just mask this signal. So as a result, like your controller is going to fluctuate very, very fast, which is not the intended result, right? But that's due to the fact that the derivative controller may amplify high frequency, low magnitude noise. Okay, so this is, we may consider it to be low magnitude, but the issue for us is that it's a low magnitude, high frequency noise. That is the problem for us. Okay, so on the other hand, like the control action, like just amplifies it, right? And we can lead into, that can lead to problems. Okay, so I'll stop here. Like please think about all these issues. We'll come back and then look at all these points once again tomorrow, and then like we'll start doing some examples. But also like just go to MATLAB and Simulink and figure out how this derivative controller is realized in practice. Do they use it as KDS or something else? Okay, please look at it and come to tomorrow's class. Okay, so what is one way by which you can remove this effect? Integration. See, I want to remove the effect of this low magnitude, high frequency noise, right? What can I do? Filter, right? You can use a low pass filter. Okay, so just check out how this derivative control is realized in MATLAB. Okay, and come and tell me tomorrow. Okay, so then you will understand what this means.